Hello everyone, welcome to topic 2.4, structures of metals and alloys. In this we will cover that metallic bonding can be represented as an array of positive metal ions surrounded by delocalized valence electrons. Interstitial alloys form between atoms of different radii, where the smaller atoms fill the interstitial spaces between larger atoms, and substitutional alloys form between atoms of comparable radii, where one atom substitutes for the other in the lattice. So on our notes, metals are composed of cations that are embedded in a delocalized sea of valence electrons. This means that electrons do not stay with one atom, rather they are able to move throughout the entire substance. The cations and the electrons are attracted to one another through a Coulombic attraction, which holds the metal atoms together. In this image, you can't tell which electron, so this one here, came from which cation. That's the idea of delocalization, is those electrons are just free-floating randomly around, acting as like a glue to hold those positive cations together, but they are kind of like a fluid and floating through everything. Okay. The number of valence electrons determines the number of electrons in the delocalized sea of electrons. When the charge on the cations and the number of electrons increases, the attractions are greater. Additionally, when the ionic radius decreases, attraction increases. So again, we're busting out Coulomb's law right here. Mixtures of metals are called alloys. They can be examples of a solution, a solid solution, which is a mixture of two different things. Two types of alloys are interstitial and substitutional. You see them below. The difference between them is the size of atoms that are being added to the metal. So in interstitial, the atoms added are small, and so they fit in existing holes. So we see them here, right? So this is interstitial. So like carbon, like stainless steel, where we have carbon embedded as an interstitial alloy in iron, like it's sitting in the little holes between all the iron atoms. That is an interstitial alloy. On the other hand, we have atoms where they have similar radii. Okay, so they're replacing atoms in the lattice. So they have to be kind of close to each other on the periodic table, but then they are substitutional. And so we see this with copper and nickel, because copper is similar enough in size to nickel that it'll just switch out. Okay. So carbon steel, like the one above in the example, is an alloy composed of a small amount of carbon atoms combined with iron. Consider the atomic radii of both iron and carbon and draw a model that describes the alloy that forms. So we're pretty much going to copy that over, right? So we have big repeating pattern of iron. And I lack artistic skill, so my carbon is just going to fit in the little pockets. So this would be iron, and this is carbon. Okay, and it doesn't have to be a ton, just enough to get the idea that sitting in there in the little nooks and crannies are some carbon atoms. So now in the we do, using the notes, please pause the video and label each one of these. Okay. So in the first one, we don't see any different atoms, we just see one, and so we can assume that that is a pure metal given the context of what we've been talking about. The next one, our second one, is a substitutional alloy, because we see that the blue elements have substituted in for some of the red ones. Then in our last one, we see little green, much smaller elements have fit into the pockets of the pre-existing pure metal, and that is an interstitial, I don't know if I spelled it right, alloy. Thank you guys for tuning in. Complete the you do, check your work, and thank you again.